Okay, let's get started. Any questions about, oh, so happy 4th of July. Hope you had fun. Any questions about the previous online lectures? Yeah.
So what's the particular follow the ATM part?
Oh, ATM proof? Okay.
So when you decided to swap that out,
So remember in the, so I have to remember this, how it goes. So let's see. So we run this supposed decider for ATM-H on this thing. And then we output the opposite. I think it's how I wrote it. So I'm not saying that this machine does anything useful. It's just, all I'm asking is, can I actually build this machine if I can build H? Yeah, the entire purpose of this machine is to help me get the contradiction. Yeah, I'm not saying this machine does anything useful. Yeah, the key is that can I build D assuming I can build H? Yeah, that's all I really need. And then we get the contradiction of D cannot exist, so there's no way H could.
So those other than future applications?
Yeah. This machine is pretty useless other than that. Other questions about the online lectures? Yeah.
I had a question about reduction and the definition.
About what?
The reduction definition.
Oh,
Another class.
Okay, so what about it?
So when we apply F, when we're doing these, when you show these proofs, F is where is F?
So it's kind of hidden.
Yeah.
So recall the ATM. Let's say the ETM proof. Then what we had was so we're trying to make a decider for ATM, correct? So we have this MW thing, and then I'm not going to go through the entire machine. But we make a Turing machine M prime that does whatever it does, and then we run some decider on M prime, and then we do some stuff based off what that machine did, right? So that's the basic structure of a reduction. So the reduction here is we're transforming this MW thing, and we're transforming it into M prime. So in here somewhere is the M and W being used. So remember we had these two different behaviors of M prime depending on what M did on W. So the reduction is we're taking this machine and string input for ATM, and we're going to convert it to a machine that has certain properties, that has either this property or some other property. In this case, we had that if MW is actually in ATM, meaning M does accept W, then this implies that the machine that we have is, I think I did it the other way around, it is not in ETM. Okay? And we guaranteed via the definition of reduction that it's an if and only if here. So if I give you an input that's not in ATM, meaning the machine does not accept the input W, then the machine I'm going to have at the end has empty language. Okay? So the key here is that the answer is preserved when I construct the machine at the end. Either it's the opposite of what it should be, or it's the same. So it's not like, for example, is this a valid reduction? So given an arbitrary MW, and I'm going to produce the string or just the result true, or except on all strings or something. Is this a valid reduction? No, why not? Yeah, what about the MWs that are not in ATM? But those are going to be mapped to true as well. The answer is not preserved. Okay? So what I'm trying to get at is that reductions try to preserve the answer. The answer of whether this original input was an ATM is the same as, or the exact opposite as to whether whether M prime is an ETM. Like another one, we had this ETM to EQTM reduction from the online video, where we made this machine that accepted nothing, and we fed the supposed decider to EQTM, the original machine, and this empty language machine. So if we have a machine, whether it's an ETM or not, then we make a mapping to this. Meaning that I make this Turing machine M sub empty, and the answer is the same. So if M does have empty language, is this pair of machines in EQTM? If M's language is empty, is this pair of machines in EQTM?
Yes.
Yeah, because they have the same language, right? So they must be in EQTM. What about the other way? If M does not have empty language, meaning it is not an ETM, is this pair now in EQTM? No, because can a machine with non-empty language be equal to a machine with empty language? I hope not. So that's why we need the answer to be preserved. So that if we could solve this EQTM problem, then we can solve the ETM problem, because I can use this supposed decider to solve it. And the answer is preserved when I make this reduction here. Does that make sense?
Yeah, I think so. Just going off of that, if we were talking about, we have the theorem as a corollary, and the theorem says if B is decidable and A reduces to B, then A is decidable?
Correct. Yeah. Those two statements are the contrapositive, so they're equivalent. That's exactly what we have here. If I can solve EQTM, meaning it's decidable, then ETM must be decidable.
Yeah.
Because that's how it goes. So the opposite of that is, if ETM is not decidable, which it is not decidable, then EQTM is not either.
And that's because if A is undecidable and A reduces to B, then B is undecidable. That A is going to map to B, and it's going to keep its undecidability within B, and that means
the answer is preserved. That's the key here. Since the answer is preserved, then we can actually do the contrapositive here. And so the decidability will hold there.
Okay. But so if we do the contrapositive, and I'm just trying to think, if we have A and A reduces to B and A is undecidable, the reason that B is undecidable is because when A reduces to B, it keeps its undecidability in B, and then that means that it's in B and that B can't be. B is undecidable.
You can think of it in terms of, well, suppose B were decidable. Then you can decide A. It's useful to think about why this works in the original direction. Like, if I can solve B, then I can solve A.
Oh.
But we use it in making these reductions in the other way.
Okay.
Does that make sense? We can talk offline if you're still confused. Yeah.
So is the EQ you're basically trying to say, because you're assuming that EQ would be decidable?
So I made this reduction. We made this reduction in the lecture from ETM to EQTM.
Yeah.
So if I can solve EQTM via whatever decider, then I just built a decider for ETM.
Like inside of your.
Yeah. So like from here, think of this example. If I can solve ETM, then I just found a way to make a solver for ATM. Right? So the same thing here. If I have a solver for EQTM, then I can make one for ETM. Okay. Any other questions? So I promised I would talk about question 3 on problem set 1. Who's having trouble with it? Not as many as I thought. So I realized that the question was way too difficult, and the reason I thought it would be easier was it's a variant on one that I know is much easier, but because it's the way that it's made is actually a lot harder than I originally thought. So here's what we're going to do. So I hope you'll be happy about this. So what we're going to do is, for now, eliminate Q3 from your problem set for now, and take the total score, not SOAR, score without Q3 out of 19. So that's something between 0 and 100%. Scale it up to 25, so scale it up, and then add the Q3 score on top of that as bonus credit. And whatever extra credit else you get as well.
So now Q3 is extra credit?
Yeah, effectively, yes. Yep. And I assure you all problem sets from now on won't be as rocky as this one. So since this class has never been taught in the way that we've done it before, it's a little rocky at the beginning, but I am very, very confident. Since we're getting into DFAs later today, it'll be much more stable. Okay, does that help? Okay, good. Any other questions about the problem set? Yeah.
I had another question about the videos from Wednesday.
Yeah.
So at the end of the ATM reduction proof, you just say that, but ATM is undecidable, so ETM must be. Is that just a consequence?
Yeah. So that's what he was saying over here. If the left side is undecidable, then the right side must be undecidable as well. Since we proved earlier that ATM was undecidable, then there's no way ETM could be. Because if ETM were, then this thing, the thing that we made in the lecture, would be a decider for ATM. But we figured out, no, that can't possibly be true. So therefore, there can't be a decider for ETM either. Okay? So it's basically a hypothetical solver to solve a known undecidable problem. Yeah, there's no way that this hypothetical solver could exist. Yeah.
I didn't actually watch the lectures, so
What should you do right after lecture?
Could you just explain what reduction is, if it's a continuing thing, like if you're going to use it today?
So a reduction basically is we're transforming one input into another input, such that the answer is kept the same, or the exact opposite. So here, we mapped this machine and input, whether it was an ATM or not, it may or may not be, but the answer is the exact opposite as to whether it was an ATM or not. So if M did really accept W, then this M prime that we make in the lecture does not have empty language.
Is it like a map? Is it like a chosen one?
It's a mapping. So it's actually usually called mapping reducibility. That's the formal way to say it, but all it is a mapping, such that the answer is preserved across the map. Or it's the opposite, of course. Other questions? Yeah.
For enumerability,
Mm-hmm.
recognizability, for the left word way, what did you do at step A on run the first I strings of sigma for I transitions using
So remember when we wanted to go from a recognizer to an enumerator. So if I just let this recognizer run, can it run forever?
Yes.
Yeah, possibly. So we need to be able to cap that somehow, because for an enumerator, it needs to, for any given string, output that string in a finite amount of time. Okay, so what we did in the proof is say, well, and we got to get to arbitrarily far strings. So we can't just focus on one string. We need to be able to work with any string that you like. So what we did is we have an enumerator, let's say, for sigma star. So maybe lexicographic order or something. And we're going to look at the first I strings. Well, if I just look at those first I strings and I run each of them via this recognizer, then the recognizer might run forever. So we cap that by saying, okay, I'm going to let you run for I transitions each. Okay? And why we do that is, well, one, to guarantee that we will stop, because I will be always finite. But another reason is if this recognizer actually will accept a particular string, but it hasn't run long enough, since this loop is an infinite loop, that the value of I will increase. But if I increase the value of I, I'm still going to consider those first I strings that I considered before. So in fact, I'm going to look at that string again and run it for longer. Okay? By running it for longer, if the recognizer will actually does accept that string for some number of transitions, I eventually will say yes on that string. Okay? So it's a way of looking at all the strings, or as many strings as you like, for as many transitions as you like, and if the machine eventually stops on those strings, I will find a number of transitions to apply to make it eventually stop. Okay, does that make sense?
Yeah, so it has like a certain size it searches, and then it searches larger,
Mhm.
larger.
Yeah.
Goes through it all again.
Mhm.
Larger.
So the key is that the enumerator actually does run forever. So even if the recognizer does not say accept on anything, then it's important that I keep trying strings for longer and longer and longer, because I need to, for any string in the recognizer's language, actually output it at some point. So it's important that I let the number of transitions just keep going higher and higher. So why not just let the number of strings I consider and the number of transitions I apply coincide with each other?
So do you call going left the enumerator and going right the recognizer?
So, or did you mean from an enumerator construct a recognizer?
Yeah. You said enumerator earlier.
This what you were referencing is this direction, from recognizer to enumerator. If you the other direction's a lot easier. I can't spell today.
Then you did the left.
Okay, I didn't know if that was the other way around. So, how did we do this direction? From enumerator to recognizer. So,
We list out strings.
right. So I'm given a string that I want to say is in the recognizer's language or not. Right? So I'm given an arbitrary string. So this is the recognizer right here that I want to build. So on input W, then all I have is the enumerator to figure out whether or not whether W is in the language of the recognizer that I want to have. So what I do is I just repeatedly list strings via the enumerator. The enumerator just tells me another string. I look at that string. If it's ever equal to W, is W in the language of the recognizer? Yeah, because the enumerator has language L, let's say. Then if the enumerator prints W at some point, is W in L? Yeah, so at that point, I just say accept, because I want the recognizer to have language L. But if it never prints W at all, is W in L? No, because the enumerator, if you pick any string you like, it will print it at some point, at some finite time. So if it never prints W onto the tape, W is not in the language. which means I'll never accept, but that's okay because I have a recognizer. Okay? Any questions about that?
Was that the easier one? And
Yeah,
then
that's the easier one.
The other one I was asking was the harder one?
Yeah, the other way is the harder one. Other questions about the lectures? Okay, there's one last thing that we need to cover about Turing machines before we go on to the next big topic. So, right at the end of the online lecture, I introduced this thing called an LBA. So, what is an LBA? What does it stand for? Linear bounded automaton, right? So, what is the difference between an LBA and an arbitrary Turing machine? Right, so the Turing machine, the standard model, goes one-way infinite, whereas the LBA, what does it have? It has a finite tape, but what is it constrained to? Where the input is, right? So if I give you a longer input, do I have more tape on the LBA? Yeah, it's constrained to where the input is and these two end markers to help you figure out where you are, because I can't actually shift the input because it's constrained. And we considered this language A sub LBA where we considered it's exactly the same as ATM, but now we're dealing with LBAs instead of Turing machines. And what did we find about this language? It's decidable, and why is it decidable? Just as a high-level idea? Right, it's a finite number of configurations. And we actually not only know it's finite, we actually know the exact number of them that could possibly occur. So we just simulate for long enough until we guarantee that we have repeated a configuration, which means what will happen? Yeah, it'll just keep doing that same thing over and over because an LBA is deterministic. So if it is in a configuration and it sees that configuration again exactly the same, it'll keep repeating that configuration over and over, and we can actually check now that it has run forever. So the difference we can see now between LBAs and Turing machines is that there are some Turing machines that won't repeat configurations, but nevertheless run forever, which is pretty interesting. So we found that the A sub LBA is in fact decidable. So now let's finish this up by talking about E sub LBA. So it's exactly the same thing as ETM, but now we're dealing with LBAs. So can I reduce A sub LBA from A sub LBA to E sub LBA, and that will show E sub LBA is decidable? Can I do it that way? So is this if we follow the same reduction as from ATM to ETM, can I do this type of reduction? Oops. And what this will show is that ELBA is decidable. No, why not? It's the other way around, right? So if A sub LBA is undecidable, then E sub LBA is decidable. If A sub LBA is decidable, which it is, does that tell me anything about E sub LBA? No. So I can't actually do that type of reduction. Of course, if I showed E sub LBA is decidable, then A sub LBA is decidable, but we already know it is, so that wouldn't actually help us. But in fact, we'll actually show it's undecidable. And so how are we going to do that? So if we want to show that it's undecidable, we need to reduce from some undecidable problem to E sub LBA. And the one that we're going to actually do is ATM to E sub LBA. And note, I'm actually saying A sub TM here. So it's important that it's actually a TM versus just an LBA. Okay, so how are we going to actually do this? So remember, a decider for ATM must take a machine and a string. And what we want to output is, so this is in ATM if and only if some machine that we're going to make based off of that, let's call it M prime, is in E sub LBA. Or not in, so the answer is preserved. So how are we going to do that? So one way we can think of this is, remember that for a reduction, or pretty much any reduction we looked at, we had this M prime machine have two different behaviors depending on what M did on W, right? It either had this behavior or it had this behavior. And one common thing, if you think back to the ATM to ETM reduction, we had this machine either have sigma star as its language or empty set as its language. So what we need here is something based off M and W that we can check using an LBA, okay? So we don't have arbitrary long tape that we can use here. We're only constrained to an LBA. Okay, so is there something that we can actually check using an LBA about a Turing machine at an input that either has non-empty language or it has empty language? And that will give us the deciding factor of whether M actually does accept W. Okay, so what we're going to think about here are, well, suppose we run M on input W. And let's say that M does accept W. How many accepting computations can M have on W? Well, certainly one is possible because M could accept W. Could it accept more than one? More than one way? Are Turing machines deterministic? Yeah, so could you have more than one computation on an input? No. Well, we know that there's at most one accepting computation. Could there be zero? Yeah, how would that happen? If it rejects or runs forever, right? Oh, 1 or 0. So maybe we can encode these computation, what are called histories, as strings, and if we can build an LBA to determine whether a given string actually is a sequence of configurations of M on W, if we can use that for an LBA, well, that language can only have one string in it or 0 strings in it. And so therefore, if we can figure out, yeah, it's not actually empty, then we just figured out M accepted W, because we just figured out there's one string in there, and that one string encodes an accepting computation history. So that's what we're going to talk about briefly. So we're going to talk about accepting computation histories. So what these are is if you think of the configurations of the machine over time, then we had this starting configuration where we had this start state and the initial input, and then a transition happened, we got another configuration, and then we applied another transition, we got another configuration, etc., until the end. So what an ACH, as I'm going to call it, is a sequence of configurations like this, where the first one is the start config. The last one contains Q accept in there because we want these to be accepting computation histories. And each of the configurations along the way will generate the next one via a single transition. So it's just a way of encoding the computation as a string. So remember back in the definition of computation, we had this list of configurations. It's exactly the same thing here, but we're just putting delimiters in between and writing it as a string. So each of these is a single transition, and then all the way through into the last one. And we know that there's not one after C sub m, because there's a Q accept in there, and we stop when we see Q accept. Any questions about this? So I actually found an error in the lecture notes for the next line. So we're going to talk about this language. So L sub m and w. So this machine's going to be dependent on what m and w are. So we're going to think about all the accepting computations of m on w. So, well, there can only be one or there could be zero. So this language, whatever it is, has only one string in it or zero strings in it. So we're going to encode this as a string such that this is an ACH for m on w. Okay, so all the possible the computation histories for which m has this accepting computation history on w. So this, as I said, this language can only have one string in it or zero strings in it. So the important question here is, can an LBA, given this arbitrary string, which may or may not be a computation history at all, can it figure out whether it actually is an accepting computation history or not? Well, let's see. Can an LBA figure out whether the first configuration is the start one? Well, what does it have to see? The first character after that number sign better be what? The start state of m. Well, it knows what m is because m is a fixed machine. So the start state's there. What must appear right after that start state? W. So what do we need to check for the LBA? That C0 is Q0W. So it's the start state followed by the input. Could an LBA look at the very last configuration and check whether it's an accepting one? Yeah. So what do I need to do here? What does an LBA need to do? Well, let's see. Just go to the last one and search for what character? What state should I see? The Q accept. So for C sub m, look for Q accept. So if it is there, then great. But if it's not there, then there's no way that this could be an accepting computation history, or a valid accepting computation history. Okay, that makes sense. Am I done checking that this is an ACH? You can tell by my tone it's not. So what did I forget? Yeah, going from one configuration to the next one. And how did I get from, say, C0 to C1? What happened? Via one transition. So, well, let's think about that. Think about where the tape head is from one to the other. Other than right around where the tape head is the rest going to change? No. So what we need to do is, other than right around where the tape head is, we need to just check if it's the exact same string on both sides, other than where the tape head is. Can we check if it's the same string on both sides of a delimiter? Yeah, we've done that several times now. So that's easy. What about right around the tape head? Well, what do I need to look up to make sure it actually is a valid transition between the configurations? Where do I look? In the transition function of the machine, of the Turing machine that we have. So to show that Ci minus 1 yields Ci, they must be the same except around where tape head is. And for there, look in M's transition function. So the exact details are not important here. What's important is, can a machine actually look up in this transition table and see, is this a valid transition or not? Well, the table is finite, so definitely a Turing machine can do it. Well, let's see. If we had a decider for, so first of all, we just were able to show that we can decide this using an LBA. So in fact, an LBA can figure out, given a machine and input, whether a given string is an accepting computation history. Well, let's see. Suppose that we can decide E sub LBA. Well, can I build this decider once I know the Turing machine and the input? Once I know M and W, can I build that machine that does those checks for me? Yeah, certainly I can build a machine that looks like this, that can do this functionality. Well, if I can decide E sub LBA, if this LBA's language is empty, what do I know about the original machine and input? Did M accept W? No, because whatever language this thing is, it must be able to say yes when there's an accepting computation history. But if it is empty, M could not have accepted W, because if it did, then there must be an accepting computation history. Okay, well, I'll flesh this out a little more. So let's see. So call this LBA, let's say B. Then if ELBA is decidable, then can build B based off of the original machine and input. Then let's see. So if the language of this LBA is not empty, then there must be some string in its language, but there can only be one, which means M must have accepted W. So then we say accept for the supposed decider for ATM. Then otherwise, if the language of B is empty, then there's no accepting computation history for M on W, meaning M could not possibly have accepted W. So reject. But that must mean we just decided ATM. And so therefore, since ATM was undecidable, there's no possible way the emptiness problem for LBAs is decidable. Okay, so I know this one's a little confusing, but are there any questions about it? Yeah.
Question, just we decided to go straight to to prove it's undecidable. How do we know that we shouldn't have tried to prove it was decidable?
So this one, I actually am quite surprised how people, when they were doing this, could actually have that insight to go through that. So I definitely don't try to expect that, but the idea is what is important and how you do this. But I definitely won't expect you to come up with something like this.
So
Yeah.
for the LBA B, it was made for just one particular N and one particular W for that demo?
Oh, which LBA?
The B.
Yeah. This B it's given a string and checks whether it's an ACH or not.
For a specific machine and specific.
Yeah. I fix the machine and input first. If I don't do that, then I don't think that's possible.
What if there's another string that's accepted on the machine? How does that?
Well, remember the ATM problem is I'm given a string, machine and a string. So I fix those two things first, then I build the machine B.
Oh, you're trying to decide, you're trying to get yes, no for one condition either way.
Yeah.
Okay.
Other questions about this? Okay, so let's go on to the next major topic. So we're leaving Turing machines behind, although you shouldn't forget about Turing machines because they'll be on the test, I guarantee. So don't forget Turing machines. But what we've been saying about all these undecidable results lately should kind of worry you, right? So we have all these many problems that we can't solve via Rice's theorem, these reduction things, these problems that people actually really care about. And showing that they're undecidable is kind of crummy, right? So what we would like is to restrict the model in a useful way so that the problems become decidable again. And then maybe we can say, well, if we restrict the model, are there some things that we lose, like some computational power? Are there some languages that we can't make something in that model for, even though we restrict it? So the way that we're going to restrict it is in the following way. So note that for Turing machines, we could read and write on the tape. So what if we remove the ability to write on the tape? We have to read the tape because we need to see the input. But what if we remove the writing ability? Well, let's see. If we move right and we hit the blanks, then what happens? Am I going to write a different symbol there? No. So if I hit the blanks and I move right, what's going to happen? I'm going to keep going. I'm never going to stop. So what we're going to do is we're going to restrict it even further. So we're going to, of course, remove the ability to write on tape. So for that reason, we can just scrap the tape idea altogether because the entire purpose of the tape is to be able to write different things on it. But we're also going to only allow moving right. This actually does not restrict the model. It seems like it does, but it actually doesn't. But it makes the thinking about it a lot easier. Well, let's see. Suppose that since we're only allowed to move right, and we see a character, and then now we move right, am I going to see that character again? No. So in fact, I only need to remember one character at a time here. So, but think about when the machine finally runs out of input. We're going to actually force the machine to stop once it reaches the end of the input, because if it hits blanks, then it's just going to continue on forever anyway. So we can't just have one state that says, I'm the accepting state, because if we're somewhere else and we happen to hit the end of the input, then we actually need to make a decision about whether to accept that input or not. So in fact, we need some more states to say, yeah, I'm an accepting state. But we actually don't need a rejecting state now, because once we run out of input and we stop the machine, we don't need a way to say, no, I reject the input. So if we end up in one of those states that is not an accepting state, then we must say no on that input. So in fact, we have a binary flag now on the state itself to figure out whether we accept the input depending on what state we land in. Okay? So the machine that we're going to be, the model that we're going to be talking about is what is called a deterministic finite automaton. And actually another great reason why to teach this in this order is that it's chronologically studied in the same order too. So people were thinking about Turing machines first, and then finite automata came about 2 decades later in the 50s. So what this is instead of having these Q accept and Q reject states and this tape moving right, moving left idea, all we have is a single character that we read between transitions, on the transition. So if we have, let's say, a start state, for example, and we want to go to another state based off what we see on the quote-unquote tape now, all we need is a single character there. We don't need to say what we're going to write or which direction we're going to move because we've removed both of those abilities. And so on top of that, if I want to say, once we read this input, we're going to stop in some state. Suppose that we happen to end in Q0 somehow, and we want to say yes on that input, we're going to put a double circle around that state to indicate that is an accepting state. So there may be more than one accept state, there may be one, there may be 0.
Why don't we just have a separate Q accept?
Because in some cases you need to be able to handle going through these states. Because that's actually an interesting question. We'll get back to that. So there's a model that's a generalization on this where you can assume you can have exactly one final state, but we're not going to get there yet. So you might as well allow multiple states to have a what is called a final state or an accept state. Okay, so let's just do an example of one. So one example is, let's say all the strings in 0, 1 star such that the number of zeros in W is odd and the number of ones in W is even. So can a Turing machine decide that? Yeah, we can certainly do that. Question.
I was going to say, it's a generalization because you get to the end, and you can see a language go with all the acceptance states go with another.
So in fact, we're going to discard like the tape completely. We're going to remove the blank symbol. We're going to remove the ability to write and move right or left. Yeah.
I mean, like when you said there's a generalization where there's one acceptance.
Yeah. Mm-hmm. So the difference is that with Turing machines, you don't have to read the entire input to say accept on that input. Like, for example, if you have the language, all the strings in 0, 1 star such that they start with 0, I just need to read the first character. I don't need to read the rest. But in this, I actually will need to read the entire input, because we're going to force the machine to read the entire input first. But in that case, what you would do is, for the language starts with a 0, then what you could do here, if we're going to force it to read the entire input, is something like this. And then 1 goes somewhere else. So here, once we go to Q1, I'm never actually leaving Q1, but I have to read the input anyway. So it just makes the model definition of computation much easier if we force it to read the entire input. But the generalization that I'm talking about is non-determinism, and we'll get to that eventually. Any other questions? Okay, well, let's see. Let's just say that I'm going to start building a DFA for this. So that's actually the acronym for this. So if I'm going to build a DFA for this, right at the very start, what is the number of zeros that I've read so far even or odd? Even. And same for the number of ones, right? So maybe what we can do is we can have a state for each of the 4 possibilities. You have an odd number of zeros, odd number of ones, even, odd, even, and both even. So this start state represents, I saw an even number of each. So maybe I can give a name to this. So let's say even for zeros, even for ones. Well, if I read a 0, what happens to the parity for 0? It becomes odd. What about the 1 parity? Does it change? It stays even because I didn't change the number of ones that I've seen. So in fact, if I see a 0, I need to have a state Q odd for the zeros and even for ones. Coincidentally, for the Q odd even state, if I see a 0 on that state, where does it go? It goes back to the even state. Even Steven. All right. Well, what if we see a 1, let's say, in the even state? What should be a state that I go to? Even, odd. Yep. And actually, for that state we just made, what about a 1 in that state? It goes back to the top. Yep. And in fact, we can keep on doing the exact same thing. And we can actually figure out, oh, the zeros move across, and the ones move up and down. Because all we're doing is just changing the parity in one of the 2 places. So we're either changing the parity for the zeros place, or we're changing the parity for the ones place. Okay, well, now what we need to do as a final step is to indicate which of the states are an accepting state. Okay, well, what state should be the accepting state in this case? Yeah, odd and even, which happens to be over here. Cool. So in fact, we could make a Turing machine for this, but in fact, we can discard with all of this unnecessary stuff about a Turing machine, and we could still build a machine that has this language and decides this language. So you maybe think, well, what can we do with a DFA now? Are there problems with DFAs that are decidable, whereas the ones with Turing machines are undecidable? So we'll actually get to that eventually, but of course, this is a formal class. We need to write a DFA definition down in a formal way. Well, let's see. Do I need states for a DFA? Yeah, definitely. Do I need an input alphabet? Yeah. Do I need a tape alphabet? No, because we discarded with the tape. What about, do we need a start state? Yep, because it's exactly the same for states. Otherwise, do we need a transition function? Yeah, it's not the same transition function, but it's a transition function. Do we need an accept or reject state? Well, we need some kind of accepting states, but we don't need a reject state or an accept state, a single one. So we need to convey a set of accepting states, and that's what we're going to do here. So a DFA is so we in fact discarded 2 things there, but actually 3 things, and we added 1. So is a 5 tuple, so going from 7 to 5. So the meanings of each of these is exactly the same, except for the last one, which I'll get to in a second. So it's a 5-tuple Q, sigma, delta, Q0, and F, where Q is a finite set of states. We all know that. Sigma is a finite input alphabet.
The N symbols in sigma now.
I'll get to that eventually. So I'll talk about the transition function in a second. Q0 is the start state. We all know that. State. Well, this F thing over here is try to convey the set of accepting states, or set of final states where the F comes from, final states. Well, what in relation does F have with the set of states Q? It's a subset. So, in fact, F is a subset of Q, is the set of final states. Okay? Let's see. Did I define everything in the 5 parts? What did I forget? Transition function, okay. Well, let's see. What did the transition function for a Turing machine have? So it took a state and a tape symbol, and it outputted what? The next state to go to, what else? The thing to write, and what else? Which direction? So we can, since we don't have a tape alphabet anymore, but I need to see what's in the input, we're going to replace tape alphabet with input alphabet. So we're going to have Q cross sigma here. So instead of gamma, it's sigma. And we definitely need to go to another state, but am I writing anything on the tape? No, and I'm not moving any direction either. So in fact, this is all we need. But since the D in DFA says what? What does the D mean? Deterministic. So what should be true about this transition function? It's a total function. Yes. Sweet. So in fact, this restriction made this definition a lot easier because the transition function's easier. We don't have to deal with this tape alphabet thing. We just need to figure out, we feed this string in, and do we land in a state in F or not, is the deciding factor of whether we accept the input or not. Any questions on that? Yeah.
What is a total function?
Total function, what is a total function? I forget, someone remind me. Yeah, so total function just means that every pair pair in this case, every pair in Q cross sigma has a defined value. So if it's not a total function, then I can find a state and input symbol where there's no transition defined. So like for instance, if I have input alphabet 0, 1, and I have a state right here, I have a transition on 0, but not a transition on 1. Is this a total function? No, because there's no transition on 1. If every state has both of those arrows leaving it, is it a total function? Yeah. So all you don't need to think about the formal part of it. Just look at every state and see if an arrow comes out on every single character. Exactly one arrow comes out on every character. Yeah.
Is there still a convention that says if there isn't an arrow, it's a reject?
No. So we'll talk about a generalization which allows that. But here we're going to, since the model's simple enough, we're going to allow all arrows. We need all arrows present. because there's no reject state anymore. Other questions? I think it's time for a break.